The human cardiovascular system operates as a complex fluid dynamics network. At its center, the heart generates the constant rhythmic force of a high-powered pump, moving thousands of gallons of blood every day. All of that oxygenated blood is funneled into a single primary biological pipeline. This is the aorta, the largest and most critical artery in the body. To withstand the heart's output, the aortic walls are built with remarkable elasticity. They must expand to absorb each high-pressure surge, and then immediately recoil to keep the blood flowing toward the organs. Because this system operates under constant mechanical stress, its structural integrity is everything. Even a microscopic flaw in the wall can compromise the entire pipeline, creating the potential for a catastrophic system failure. That failure begins with material fatigue. Over time, the repetitive pounding of blood pressure can wear down the elastin fibers in the aortic wall, creating a localized weak spot. As this structural vulnerability develops, it triggers no external alarm bells. There is no pain, no physical sensation, and no outward sign that the arterial wall is beginning to give way. The danger stays hidden until the weakened material crosses its ultimate breaking point. If the wall ruptures, it causes massive internal bleeding that can become fatal in a matter of minutes. This information asymmetry makes the condition uniquely dangerous. Since we cannot feel the pipeline breaking, identifying the threat depends on understanding the mechanical forces that cause the wall to fail. In a healthy artery, elastic tissue safely absorbs blood pressure, but a weak spot changes the vessel's physics. Constant internal pressure forces the tissue to balloon outward. As blood pressure forces the bulge further, the wall becomes thinner, leading to a rapid, self-reinforcing expansion. An aneurysm is a self-accelerating loop of mechanical failure that continues until the structural integrity of the wall is completely lost. To find these weak spots before they fail, doctors must look through solid tissue to evaluate the integrity of the hidden pipeline. They use specialized imaging tools to bypass the lack of symptoms, employing ultrasounds to check the abdomen, along with high-resolution CT and MRI scans for a more detailed view. These scans provide quantitative data to assess risk. Doctors use 3D models to measure the exact millimeter diameter of the bulge's widest point. By comparing scans over time, medical teams plot a trajectory toward a specific rupture threshold. Tracking this growth rate is the only reliable way to predict a catastrophic failure, allowing for medical intervention before the wall reaches its limit. For smaller aneurysms, the primary strategy is pressure management. The goal is to reduce the load on the aortic wall to prevent it from thinning further. This involves specific lifestyle adjustments to lower mechanical stress, controlling blood pressure through medication, quitting the habit of smoking, and managing physical activity to avoid sudden spikes in pressure. However, if the expansion rate shows the pipeline is nearing its breaking point, the strategy shifts from management to direct intervention. Surgeons perform a structural reinforcement by grafting a synthetic tube into the damaged section. This graft acts as a new inner lining, bypassing the weak spot and carrying the pressure of the blood flow. This biological engineering feat effectively replaces the failing section of the pipeline, restoring its original strength and preventing a rupture. Preventing these failures starts with proactive maintenance to stop weak spots forming in the first place. This means monitoring the variables that contribute to arterial decay, managing cholesterol, and maintaining a healthy weight, and being aware of any family history of vascular weakness. Because an aneurysm remains asymptomatic until the moment it fails, screening is the only definitive way to catch a vulnerability early. An aortic aneurysm is a silent physical threat, but by monitoring our baseline health and utilizing modern imaging to inspect the body's internal infrastructure, we can successfully identify these mechanical failures and diffuse the threat before it ever reaches the breaking point.